So today we are going to build on the foundation that we had on maintenance planning, whereby today we are focusing on maintainability and reliability assessment, which is module 3. And the objectives of today's module, I expect by the end of this lecture to be able to define what reliability and maintainability are and understand the importance in your field, and also to be able to identify the key measures for both concepts. For instance, the mean time between failures and the mean time to repair, and also being able to apply the assessment methods that we're going to look at, and also being able to evaluate case studies and practice exercises so that you can certify your understanding. So today I need your maximum attention. If you need to grab a paper, grab it and a pen, because we are going to have some exercises, and of which I expect you to participate. So let's look at what these concepts are. So first of all, let's look at reliability, of which reliability refers to the probability that the system will perform its intended function without failure for a specified time period. So we for reliability, we expect that under given operating conditions, for instance, an electrical engineer, an example I can give or an analogy that I would want you to put into in mind when it comes to reliability is assume of let's say a power supply unit, let's say in a server room. So its reliability is more on the probability that it will continuously deliver the 24 VDC to the server without failing. That is reliability. Let's say for 5 years without failing. Then a high reliability in that instance would be the component would be reliable, not being for you, the user or the end user, not worrying about breaking down so often. And for the case of maintainability, it refers to the probability a system can be restored within a specified time when maintenance is performed. So think of the same example I've just given of a power supply unit. So if it fails, let's say it fails, how quickly can it be replaced? So if the unit is modular and is accessible, you can probably swap it out, let's say in 15 minutes. And if it is not a modular unit, whereby it is deeply embedded in complex racks and so forth, so it may take you longer, like let's say 5 hours for you to rectify the issue. So which means the second scenario demonstrates the higher maintainability, whereby it requires a lot of time for you to repair it. So we need to understand that both concepts of reliability and maintainability, they help us to determine the system availability and life cycle performance. So an analogy here that you can think of, it can be, let's say you have an inverter. So for reliability is how rarely this inverter trips, you get. And then for the maintainability aspect, you can look at how quickly can you return it, to service. So think about that using that kind of analogy. So we have different measures. When you talk about reliability, we need to know specific metrics, how to quantify it, and it brings us to reliability measures. So of which we have the failure rate, which is represented by lambda, and refers to number of failures per unit time. So then we also, maybe I can give an example here, because we are going to have a series of calculations, and that's why I was like, if you have a pen and a paper, grab it. So For example, if we have, let's say, a batch of 1,000 identical lead, uh, whereby they have two failures over a period of time. I tried to use the whiteboard here, but it was failing me. So that's why I need you guys to be attentive today, because I'll be explaining everything. And later on, I'll share a book with you whereby you can go and look through the things. So I was giving you an example of whereby, let's say you have, how do we calculate this failure rate? So let's say you have a batch of, let's say 1,000 identical lead, that is light emitting leads, of which they have two failures over a period of time t. So the failure rate is the number of failures divided by the number of lead that you have, then per unit time. So that's how you get the failure rate per hour. So for instance, in electrical components, the failure rate is often assumed to be a constant. So during the component's useful stage, that is when the component is fully functioning. Then the second reliability measure, we have the mean time between failures. We are going to be looking at it so often in this lecture, of which this refers to the average time a system operates between failures. So it is the inverse of the failure rate. So if you can note that down, it is the inverse of the failure rate, which means it is 1 divided by lambda. So, so this is very common metric when it comes to electrical engineering and electronic equipment when you want to find out the mean time between failures. So calculate the failure, have the failure rate, and then for it, it is the inverse of failure rate, 1 divided by lambda. Then we move to the third reliability measure, which is a reliability function. It is represented by R of t, which is equal to exponential of negative lambda times t. So this function gives the probability of a system operating without failure up to specific time t. So for a constant failure rate, the function is given by that formula that you're looking at. You can note it down. So it means if you have, if your system has, let's say, a failure rate, which is lambda, let's say it is equal to 0.002 failures per hour. So the probability of it surviving, let's say, for 100 hours is you substitute in R of t, then you have the exponential, which is a constant, then you have the failure rate you substitute in, then times the time. And then you get the value, you can even put it in percentages. So which means that percentage will be the probability of that equipment surviving or being able to be used. And also we have the bathtub curve, of which for it is it is a classic representation of components failure rate over its lifetime. So for this one, it is a curve of which I believe the book I'm going to share, you're going to look at these amazing curves and you'll be able to understand. So I'm just introducing you to them so that you understand how they work. So under the bathtub curve, we have the infant mortality, of which these are the three distinct phases that we have under the bathtub. So the infant mortality refers to that high initial failure rate due to manufacturing defects. This occurred in the factories before the equipment even is installed and all that. Then for the useful life, basically this refers to raw and constant failure rate. this often occurs when after a certain period of time for operation. Then the way out, as you all know, it is basically about increasing failure rate as the component ages and degrades. Yeah, so this takes us, because we've finished the reliability measures, then how do we also quantify the maintainability? So these are the maintainability measures. One, we have the mean time to repair. I want you to note that for the reliability, we have the mean time between failures as one of the measures, as we've seen up. Then for maintainability, we have the mean time to repair, of which refers to the average time it takes to repair a failed system and restore it to a working condition. So I need you to know that this time also includes the time of diagnosis, how you're diagnosing this issue, trying to find where the problem is. The troubleshooting time also is included in here, and also the actual repair itself. So this means that when a raw MTT is a sign of high maintainability, because if it takes you a long time to repair this issue, it means the maintainability will go high. So the second measure of maintainability, we have probability to repair or probability of repair within specified time, of which this measure it answers the question that what is the probability that we can fix this system in less than a certain time? Because the lesser you take to fix the system, the better, and the lower the maintainability. So let's say you have to take 2 hours to fix a component or equipment. So a system with high maintainability would have a higher probability of being repaired quickly. So if the probability of repairing an equipment so easily is low, it will give you a higher maintainability. Because, as engineers, you need to make sure that your equipments are up running. So if it fails and then takes ages for you to repair it back, it means it requires a lot of maintainability, and to cut off everything, let's say the system will be down, and we are looking at being able to have less downtime. Then the third measure, we have factors, of which these factors, we are looking at factors influencing maintainability. So, of which these are several design and also operational factors that affect it. And one of them is accessibility. So accessibility refers to easy to get the components. So think of it as, for instance, a fuse box in a car, or versus a circuit board in a satellite. So which one is very easy to access? Because also accessibility matters. If it is hard for you to easily access the component that has failed to work, it means it's going to take you longer. So you need to keep in mind that accessibility is also a key aspect when it comes to maintainability. Then we also look at the tools. So tools and spare parts, they are very necessary, tools readily available. You make sure that the tools and the spare parts that you need are available in case the components fail, so that you don't wait for the components to fail or the equipment to stop running and you need to replace and you don't have spare parts. That's when you start thinking of to buy spare parts or to order for spare parts. So that is not good for an engineer to do. So again, you need also to look at human skill. So does the maintenance technician, do they have the required or necessary skills and training to perform this repair? Also need to look at that. Then lastly, the task frequency and ease of maintenance operations. So you need to look at Maintenance operations, like straightforward, are they documented clearly? Do they keep records? So that is also critical to look at. And then this brings us to availability, of which we've already seen up that these concepts of reliability and maintainability, they give us availability. So what is availability? So availability represents the probability that the system is operational and ready for use when needed, as you've already seen. So it has that formula of which availability is equal to mean time between failures, then divided by mean time between failures plus mean time to repair. So it combines reliability, which is more on failures, and maintainability, which is more on repairs. So which means a high availability requires both fewer failures then plus faster recovery times. As you can see from that formula, you can see that mean time between failures divided by, so availability is an inverse of MTTR. You can see that. So it means the when MTBF is high, availability is also high. When MTTR is high, then to affect availability to be low. So key metric for operation systems like power plants and communication networks. It is very key because these components, these systems, they have to be up running 24/7. So in case there is a problem with them or any components or any malfunctioning, we expect this to be restored in the shortest time possible so that they can run again, because it affects a lot. Imagine if the communication network is off for days, how it will affect. So I'd want you to think of, maybe let me ask you something. If what happens if I reduce MTTL without changing MTBF? What happens to availability? Can someone talk? If I reduce the mean time to repair without changing the mean time between failures, what happens to availability?
The availability
Variability is a
increases.
bit increased.
I didn't hear you.
The
Variability is a bit
availability
increased.
increases
Why?
because when we increase MTTR,
Mm.
then even if we don't increase the MTBF, here since it's a fraction, so here our denominator is going to increase, and if the denominator increases, that means we are if the denominator increases, that means we are reducing our variability.
Great. At least someone is following. So that's right, availability increases because if repairs are faster, even if failures occur at the same time, like at the same rate, you can easily repair. So increasing the availability. And as I've already explained, when you look at that formula, you can see the inverse proportionality. So if MTTR reduces, then it means they will increase and vice versa. So let's go to assessment methods, of which we have 5 different assessment methods. So one, we have for assessment methods, think of them to the best way how to accurately measure reliability and maintainability. So of which we rely on this below that we are going to go through. One is statistical analysis of failure and repair data. So for this, basically, we use statistical tools analyze the real world failure and repair data to estimate the MTBF, MTTR, and failure rates. I hope when I talk of MTBF, MTTR, you guys understand because you've gone through that. So this what it does. It involves collecting data on component failures. You collect that data and repair times. How many times have you repaired the equipment? And then you record. So it can also helps you to assess how the equipment or the system has been performing, let's say for a specific time period. Then number two, let's look at reliability block diagrams, or call them RBD, of which this is it is a graphical method where we use it for modeling the system's reliability. So what it does it shows how the reliability of individual components for each individual component, how it contributes to the overall system reliability. Because for a system has multiple components, so it's a collection of different components. But for RBD, what it does, it gives you the information per individual component, how it is performing. So it is a series of arrangements of which it is less reliable than its least reliable component, while parallel arrangements is more reliable than its. So what you do for reliability also depends on the arrangement of these components. Are they in series? Are they in parallel? Of which, for best practice, recommend parallel connection. Of reason being, for the parallel arrangement is more reliable than its most reliable components. Then number three, let's look at fault tree analysis, or FTA, of which it is for it is a top-down deductive method, whereby you start with top event. The top event here, for instance, we are looking at the system failure, and you work backward to find all the possible component failures or human errors that could have led to the top event. Then this particularly is useful in software critical systems to identify and mitigate risks, whereby you start where the problem is. You have the problem. This is why it is called the top down. The problem has failed. Then you go down to identify what caused this problem, and then you find ways how to mitigate it. So it's like a tree analysis from up, down, or top down, deductive. Yeah. Then we have simulation and prediction methods, of which here basically we can also use computer models to simulate system operation, whereby basing on the data you collect on all that, you can predict its reliability and maintainability over time. Because these computers be recording how each component performs, storing the data, the behavior, they also do self-diagnostic, whereby that data is recorded and then it can tell you if the equipment is fine or it is reliable, or if it needs to be maintained over time and all that. So it's easy now. There. Then lastly, we have the life cycle cost analysis. So this method, what it does, it helps you to evaluate the total cost, of a system over its entire life, whereby it includes the design, the operation, all the maintenances that you've done, the disposal costs. So, which means when high reliability and maintainability are very key when it comes to LCC, because at the end of it all, you want to evaluate how much you've spent on the system, equipment, all the way from its entire lifetime. So that's how you measure that. So as electrical engineers, you don't just fix systems, but you need to design them And to design them, it's a key part for your role to design for reliability and maintainability. So this brings us to design for R&M. So R represent reliability and maintainability. So what are some of the things that you need to consider or to look at when you're to design a system or an equipment? One, use of redundancy for critical components. I hope everyone here is familiar about what we mean for redundancy. So for critical components, we can use redundancy by arranging them in parallel configuration so that if one fails, the system continues to operate. So this is very fundamental concept in power systems for you to have a redundancy layer. Yeah, so that when one fails, then you switch to the next one. So that's why the parallel configuration is recommended for this. Then number two, simplify and standardize design modules. So this is more on modularity and standardization. So by simplifying the design into modular units and also being able to use standardized components, so we make repairs faster and easier. Yeah, so this is why many industrial controllers, if you can see them, they usually plug and play modules, whereby if this module is faulty and needs to replace, just remove, replace with another one. So that design is more simplified for someone to easily maintain. So making the MBF low and doing so availability goes high because it takes less for you to maintain. Then we look at easy access. Provide easy access for maintenance tasks. So here we are looking at designing systems with clear access points, yeah, and layouts, which helps in reducing the time spent, yeah, on repairs directly, lowering the MTTR. Yeah, if you spend less time on repairs, so it means the mean time to repair is low. And doing so, it increases availability. So these are the things that you need to look at when you're designing. Then also built-in diagnostics. Yeah, being able, this is more on integrating diagnostic and test failures. So it allows, what it does, allows the system to self-report faults. And in doing so, it accelerates the diagnostic process, whereby the equipment itself diagnoses itself, as we've seen and talked about this so many times, and then it records this data. So when you're coming to maintain, or if anything is wrong or it is fault or it is malfunctioning, you can easily know where the problem is. So it eases work. This comes easy for you to know where the problem is, not going into the hurdles of troubleshooting diagnosis, you know. So in doing so, it means you have to spend less time to repair because you know where the problem is. And lastly, training and documentation. It's good to provide, as a designer, provide clear manuals and training to ensure that maintenance is performed correctly and efficiently. Yes, manuals, because let's say you buy an equipment, what the first thing to look at is the manual. So most especially, don't assume that someone who's going to buy this equipment, they're like experts in how this is integrated or how it is used. So it is very key, provide clear manuals and also training if it's possible. Training to ensure that this maintenance or the usage of the equipment itself is performed correctly and efficiently. So I'd like us to pause a bit and go through this case study. This is just for us to be able to apply these concepts to real world examples. So this is an example from oil and gas industry, of which we have a system. And this system is represented by oil and gas pump system. and had a problem, of which the problem was the pump frequently experienced seal failures, leading to significant downtime. So the MTTL, the mean time to repair, was high, very high at 8 hours. Yeah. And primarily because the seal was very difficult to access and repair. Because we talked about accessibility. And you know what happens MTTR is high, as we've discussed. So what should we do? What should be the solution for this? So the solution was they used the modular cartilage seal design. So this was a new design they had to incorporate in. So it allowed the entire seal assembly to be quickly replaced as a single unit rather than having to be rebuilt on site. We've already seen the modular, the plug and play, whereby it is very easy to remove and replace and takes less time. Then what's the result here? What are we looking at? So in using this new design of modular cartilage seal, the MTTR reduced to 1 hour. Is it from 8 hours to 1 hour? So what are we trying to do here? We are making the availability of the system, the oil and gas pump system. So which means the availability was improved. So the design improvement dramatically enhanced the pump's maintainability. Yeah, so which means the MTTR was reduced just 1 hour and the overall system availability improved significantly. So this is a perfect example of how designing for maintainability directly impacts operational efficiency. Okay, hope that was easy to follow. Then we have a practice exercise. Yeah, I don't know if you guys have calculators with you, but we're going to go through this. For more examples, you'll find them in the ebook that will be shared to you. So we have that example. A generator has MTB, which is got 500 hours, and MTTL, which is equal to 5 hours. Calculate its availability. Can you guys do that? Do you remember the formula?
Yes, we do remember the formula.
Okay. Calculate. Calculate and give me your value in percentage.
Okay.
1 minute. Let's substitute in.
You can post your answer in the chat to
Yeah,
be
I
active.
think so.
Yeah.
But I'll wait for 1 minute before I continue. So guys, just substituting and your answers in your chat. I don't know if I can access the chat though.
You try accessing the whiteboard. I enabled it and see.
Okay, I tried and it was failing me. Oh, let me try again and see.
%99.
You said you post it in the chat for the meantime. Whoever calculates, put the answer in the chat. Then you can be asked to speak later if you have to explain your answer.
No, it's failing.
The whiteboard is failing again.
Yeah, it's failing. It's failing.
I don't know what's up with this.
I don't know.
Allow participants. Are you sure? I see it enabled this side.
Can you try to see if it is working?
Yeah, it's working. I think I'm going to share it. Open.
Hmm.
I've put the link in the chat for the whiteboard. Try to click on it and see.
Okay. Anyways. Yeah,
Can you see it?
Yeah,
Okay.
let's take as ages. Okay, I see 5 people have responded. 5, let me see. 5. 1, 2, 3, 7. 7 people. How many people do you have in this class? Hmm?
We have about 30, but I can see 18 logged in.
And 7 have responded. Okay, let me share my screen again. Oh, is my screen still visible?
I think when there is whiteboard and
Ah,
I don't know whether both of them
Just
can
like
be
the
shared.
whiteboard.
ah, well,
So I first
okay.
stop the whiteboard.
But
You stop the whiteboard because it's gonna steal me.
Okay.
I'll try to explain. Maybe they can follow along.
You try to share the screen.
Uh, just
yeah, now we are back.
okay, okay. That's responded. Yeah, well done. Well done. Yeah, at least I have people with me that are following. Yeah, that answer is correct. 99%. And is there anyone who can explain what that means, like the interpretation of that? What that 99% means? Okay, so that we don't take time. So that means that the generator is expected to be available 99% of the time. Hope that makes sense to you. So since we have the formula for those who didn't participate, availability equaling to MTBF, then you divide by into brackets of MTBF plus MTTR. Remember, we have the values here, MTTBF, which is equal to 500 hours, then the MTTR, 5 hours. So you have 500, then you divide by into brackets because those are two variables that you're adding up. So it would be 500 plus 5. So it would be 500 divided by 505. So it will be equal to 0.99901. Then if you want to get the percentage, you multiply by 100. So that's how we ended up on 99%. And as I've already said, the interpretation is that is the percentage that you expect your generator to be running, to be available for use. For variability, it means it is not, it is ready to be used. It's not faulty at all. You can just switch it on and it runs. Then we have number 2. A system has lambda of 0.002 farads per hour. And we are expected to find the reliability R of t after 100 hours. I don't know if you still remember the formula. Let me take you back shortly on this. So reliability function, you see that R of t? Get that formula because I want you to give me the value. I want you to do it yourself. You've gotten the formula? Okay. So let's run to our question. So substituting, we have all the values. We have the lambda, which is equal to 0.002 farads per hour. Then we have the t. Substituting, tell me the values quickly. Because when you're doing this, you all need to
The value is 0.818873.
Okay, thank you. Others do. Also post in the chat. Hurry. You have 1 minute to do that. You need to understand the things from here so that when you're to read on your own, you still remember how we did. So and also be thinking about what that value you've gotten, what it means in this case. As we explained for the first question, that value was the probability that the generator has to be available of its time. So think of that value that you're going to get for number 2, what it means. How do you interpret that? Are people posting in the chat or? Okay, let's go on. Anyone to tell us the interpretation of that value?
Morning, this is Junior Humza.
Go on.
Yeah, the way I can interpret this is that the probability of a system operating without failures is about 87%, which means that the system cannot operate without having breakdowns at a certain moment.
Yeah, exactly. So it means approximately to 81%. That is 0.81, yeah. So it is 81.87%. So it means that probability, that's the probability the item or the equipment survives for 100 hours without failure. So that's right. So, okay. Let's go to, I hope I came about those answers and the interpretation. So number 3, suggestions or suggest one design improvement to enhance maintainability. So this one is more, as we've seen before, when it comes to design improvement, it's more on making sure that availability is high, reducing the MTTR, and increasing the MTTB. So the recommendation, it can be, for instance, modular cartilage, like we've seen for the case study that you've seen, whereby for the modular cartilage design for wire components, like you can just remove the modulars and easily plug in new ones, replace, so which makes it easy. And why it helps, it reduces the assembly time and also special tooling, whereby then in doing so, it lowers the MTTR. And again, it is also good to make sure that you provide a clear labeling and access of equipment, or let's say if it is a panel, how do you access it for fast isolation and extraction? That is also critical. And also, as you've seen, the diagnostic, like self-diagnostic, being able to add the built-in test, we call it BIT, built-in test, diagnostic, the speed fault isolation, and easily for you to trace out where the problem is, because it does the diagnosis for you and provides you with that data. And also being able to standardize fasteners and connectors so that you reduce tool changes and errors. So it's more on accessibility, it's more on labeling, self-diagnostic, so that if you're to maintain it, it is very easy for you. Easy maintenance, reducing the failure times so that the availability is high. Okay. So let's look at modeling time to fast failure. So as we've already discussed about the reliability with that function, of which it assumes a constant failure rate. But when you are to go into the real world systems and how to apply, we often have rates that change over time. So this formula is very great for high level understanding because of it assuming a constant failure rate, which is ideal state for most systems during their useful life. But then we need to understand and we need to think that what happens in reality. What about when components are new and have a high risk of failure due to maybe manufacturing defects, or it can be when they are old and just starting to wear out? So it means this model falls short. So it doesn't cater for those. So what do we do? This brings us to a more robust approach, whereby modeling time to fast failure using more advanced statistical distributions. So we look at this new model called the Weibull distribution. So the Weibull distribution is a versatile model that is used for most reliability analysis. So it is very important model when it comes to reliability engineering, and it caters for those aspects that the reliability that we solve at first, which assumes that there is a constant failure rate, doesn't cover. So it comes with 3 phases of classic birth curve that we had already covered up: the infant mortality, useful life, and wear out. So it comes with this value, beta. So it is in three aspects, whereby it has when beta is less than 1, when beta is equal to 1, when beta is greater than 1. What does it mean? So when beta is less than 1, then the Weibull model, what it does, it describes like a decreasing failure rate, whereby in this case it will represent the infant mortality stage, where early failures often occur. Let's say due to manufacturing flaws, it can be initial stress. Yeah, so for an electrical equipment or component, this might be a weak solder joint. Yeah, that fails in the first few hours of operation. So you see, then it also helps us understand the useful life when beta is equal to 1. So the failure rate in this case is constant when beta is equal to 1. And failures in this stage are random and they're unpredictable. Yeah, maybe they could be from can be maybe a sudden power surge, or it can be unexpected environmental stress. Remember, at useful stage, you expect the equipment to be running fully, no failures and nothing of the sort. Then the third aspect is when beta is greater than 1. So the failure rate increases over time. So we are looking at wear out in this case. So modeling the wear out phase. So this is when components fail, when they have aged. It can be fatigue that is running for longer hours. Yeah, it can be material degradation. Yeah, think of a relay. Think of a relay, for instance, like whose contents are slowly degrading over years of use. So that's what happens when it comes to wear out and when beta is greater than 1. So that is the Weibull distribution, which is very key to help us understand the three phases of classic bathtub curve without needing multiple formulas. So it comes in to cater for those aspects. The R of T that we saw, that formula up there, is not considering, like, doesn't fully cover. And then we also have the long normal distribution. The long normal distribution, of which for this is another powerful model that is particularly useful for modeling failure mechanisms that are often driven by degradation process. Yeah, for instance, think of the gradual growth of maybe a crack in a component. Yeah, it can be due to fatigue. Yeah, it can also be a very common model for repair times. So this is how this long normal distribution comes in. So how do we choose? One thing that we need to know is, as we've seen these models, so how do we choose which model to use? So what you do, you don't guess, yeah, of which you use a tool called the probability plot. Yeah. So it is a special type of graph paper that whereby you plot there that transforms a distribution into a straight line. So for example, if you plot your component failure data on a Weibull probability paper, and the data points form a straight line, so you can be confident that Weibull distribution is good model for your data. So what you do, you can then use the slope of the line of estimate so that you can shape the parameter better. So this is practical and data-driven, based on the data that you collect. And it is very reliable when it comes to engineers to do so that it is not guesswork, but it is all the way from the data you've collected from your components, then you plot it. If it gives a straight line, now you know what it means. And then you calculate the slope, then to be able to give you the beta value. Then for more details on these graphs, hard plot and worked examples, as I've already said, we shall have a textbook that will be shared for that. So now this takes us to maintainability engineering process, whereby here we are trying to connect the concepts that we've already seen about reliability to our new key topic of maintainability and how to connect things. So maintainability is different from maintenance, whereby maintainability is a design characteristic, not a maintenance action. So it must be engineered into the product all the way from day one, all the way in the industry or the factory it is being manufactured from. So understand that maintenance is just act of fixing or repairing a failed system. So it is reactive or planned work, whereas maintainability is, on the other hand, is an inherent characteristic of system design. Yeah, that determines, let's say, how is the economically it can be maintained. So it is not an afterthought. No, it is a design phase discipline. Yeah, that must be integrated in the product life cycle all the way from the beginning. So that's, you have to note that. So what do we look at in these processes? Number one, you translate customer needs. Yeah. So the process begins all the way by taking broad customer desires. Let's say, for instance, the customer says, I want it to be easy to fix. And so what you do, you turn the customer needs into quantifiable maintainability requirements. So for an electrical system, this might be specifying a maximum, So if someone said, I want it to be easy to fix, quantify that into something that is quantifiable. And let's say maybe specify a maximum or something like that. Then we have integrate into design. So here we are trying to ensure maintenance considerations whereby they're part of the core design process, how they work alongside reliability and availability goals. So for instance, here think of designing with modular components that can be swapped out easily, using standardized connectors and also being able to have clear visual labels. Then 3, you need to be able to validate through analysis and testing, whereby here you can use prototypes, simulations, and testing to uncover and fix maintainability issues. Yeah, before full production. So here, basically, we don't wait until the product is sold. No, we build prototypes whereby we use testing, computer simulations, and analyze to validate the design choices. So this helps you to do what? To catch and fix problems before they become expensive field issues. So you do it all the way in the factory where it is done, because once they manufacture something, they need to test it do a lot of simulations to see putting it in a situation whereby maybe it looks like a field where it is supposed to be, and then you see how it will perform. And lastly, we look at monitor operational performance, whereby here basically use field data from maintenance records as a feedback loop for continuous improvement and future design. So when a product is in the field, so what do? We collect data from maintenance records and fault reports, because as we've already seen, recording this data is very critical when it comes to maintainability and all that, so that you know to understand how the equipment behaves and how it has been performing. So this is a real world field data whereby it helps you to get this variable information that you can use to refine product design in the future, and also it helps you to complete the cycles and drives continuous improvement so that you be able to produce products that are even better than the last one that you did. So it is continuous improvement in this case. So in summary, reliability, as we've seen, is all about preventing failures. Yeah, so it is a measure of how likely the system is to perform its function, yeah, without a fault over a specific time. Then maintainability is about what happens when a failure does occur. Yeah, so it's a measure of how quickly and how easily that system can be restored to an operational state. So availability finally is a grand metric whereby, as we've already seen, it combines the effect of both reliability and maintainability. And a highly available system, we need to know that is the one that is not only fails less often, but also gets fixed faster. So those are the key things to note. So it is the most practical measure for many of the systems that you work with. Yeah, from power plants to communication networks, because it tells you the percentage of time the system is actually ready to do its job, as you've seen from the examples that we've worked on. And also moving beyond these definitions, we've even dived into how to quantify and measure these concepts. Also, we've discussed the models, the variable distribution, and all that. So we need to keep these principles of reliability, maintainability, and availability at the forefront of your work, so that you can be able to design and manage electrical systems that are not only effective in their function, but also highly efficient and cost-effective throughout their entire life. So that's all for today. I've put some discussion questions for you to guide your reading. So thank you.